This presentation is going to review the Borescope procedure for the Mars turbine. It is limited to a standard Borescope inspection. From time to time, issues will arise due to changes in the manufacturing process, design changes in materials, parts upgrade, etc. You will expect that a turbine will have all its issues resolved after a couple of years in production, but there will always be some issues. The end user are often unaware of these issues, but they will be known to the solar field service. They are privy to this information, which normally comes in the form of a tech letter. It's for solar personnel only. If solar does share information with a customer, it will be by means of a service bulletin. A Borescope inspection can be very intimidating for a new technician, but if you master the basics, you will be able to carry out a Borescope inspection on any turbine, given some minor additional training. A cross-section of the turbine is very important to have at hand. You need to know what to expect when you insert the Borescope in the turbine. It is also invaluable when you have to navigate inside the turbine. It is important not to get too ambitious trying to get into places where you might get your Borescope stuck. Not only will you face an expensive repair of the Borescope, the turbine may very well have to go back to solar for disassembly. The Borescope inspection is normally carried out every 4,000 hours, but may have to be done more often if damage is found. At the other end of the scale, some operators accumulate very little hours in service and may take years to accumulate 4,000 hours. In a situation like this, it is necessary to do a partial Borescope once a year. The internal part of the turbine may corrode, especially in salt-laden atmospheres. Compressor front section. The Mars has 32 Borescope ports and 39 other inspection locations. It was designed with sufficient ports to allow a complete inspection of the internal parts. Starting at the front of the turbine, an access panel on either side of the air intake is removed to reveal a protective mesh that protects against foreign objects entering the turbine. Remove this mesh for easy access for your Borescope. Entering from the front of the turbine gives you access to the first and second stage rotor blades, plus the IGV and first stage VGV. Let us talk a little about the naming convention for the compressor staging, as it can be confusing. Here we have the rotating blades. This is the first stage, second stage, third, fourth, fifth, all the way back to the 15th stage. This part is straightforward. There is, however, some confusion when we get to the non-rotating stator blades. The first stage is the inlet guide vanes, known as IGV. As the air comes in from the air intake, the first non-rotating blades it will come across are the inlet guide vanes. The second stage of non-rotating blades are called the first stage VGV, variable guide vanes. The next stage of vanes is the second stage VGV, etc. This can be confusing, and it would have made more sense to name the IGV first stage vane and to call the first stage VGV the second stage vane, etc. But this is the system we have, so be careful when making out Borescope reports or interpreting the reports of other people, that you use the correct name, which ensures the person interpreting the report is thinking about the same location. Moving back along, we have the third stage VGV, fourth stage VGV, and fifth stage VGV. This is the last stage of variable blades. The next stage back is the 6-stage guide vane, all the way back to the 14-stage guide vane. And the very last one is the exit guide vane. This is what they're called, and it is what you must use in your report. The next point to discuss are the bushings on the variable vanes, all 6 stages. There are outer and inner bushings which allow smooth movement of the blades. The 6th stage does not have an inner bushing. These bushings need to be evaluated during the borescope inspection to see if they are very dirty, or that there is a buildup of dirt, corrosion, or deposits such as salt. These bushings can get so fouled up that they seize up, causing the actuating lever to deform and break. An external inspection of the angle change mechanism should be carried out while doing this borescope inspection. This loss of movements prevents the blades moving and choking the airflow during low speed. This can cause a local stall event of the airflow, and if it is serious enough, it can lead to a turbine surge. The following is what you need to look for during the borescope inspection of the compressor. Note the condition of all stages of compressor and take photos which you will need to use in your report. Look for cleanliness of the compressor. This will give you an indication of the effectiveness of the air intake filtration system. It may also be a guide to the interval you need to use between compressor washes. Note any oil leaks. If the early stages of compressor are coated with oil and dirt sticking to the blades, it is most likely that number 1 bearing seal is not in good condition. If you see oil at the aft end of the compressor, it is more likely to be the number 2 seal that is leaking. Each rotor blade needs to be inspected for cracks. No cracking is good, but cracking at or near the blade root is of concern. The danger of a blade breaking away from the root is high. This would most likely totally destroy the turbine. Look for any impact marks arising from items going through the compressor. It may be an indication of more serious damage further back along the turbine. Look for any blade tip rubbing. Note and photograph any blades found with this damage. Normally this is not an issue as long as large pieces of material are not being liberated. Loss of material due to cracking, impacts, this needs to be recorded and photographed. Corrosion and erosion needs to be recorded and monitored. Sea atmosphere can be harsh on metal surfaces, and poor air filtration allows particles to enter the airstream and erode blades. Before we leave the compressor section, let's take a closer look at oil leaks from number 1 and number 2 bearing seals. First, let's take a look at number 1. Here we have the thrust bearing for the gas generator, and behind it the number 1 bearing. Behind the number 1 bearing we have the labyrinth seal for the number 1 bearing. Oil comes into this area here to lubricate the number 1 tilt pad bearing and the thrust bearing. After it has lubricated both, the oil falls by gravity into the accessory drive gearbox and back to the tank. There is a possibility that the oil could get between the shaft and the labyrinth seal and enter the airflow and contaminate the static and rotating blades. To help the labyrinth seal, we pressurize the seal with 11th stage air. The air flows into the middle of the seal and flows out either end to prevent oil from entering the seal and leaking past it. Let's take a look at the number 2 seal. This is the number 2 bearing here, and you can see the end of the compressor here. And you have the number 2 labyrinth seal here. The lube oil supply comes to the top of the compressor in a flexible hose, and then internally by transfer tubes. It then splits into 2 flows. It goes to the right to number 3 bearing and to the left to number 2 bearing. After the oil is finished lubricating number 2 bearing, it will fall by gravity and flow back directly to the tank. It joins with the oil returning to the tank from number 3 bearing. The number 2 labyrinth seal is fitted here, between the rotating gas generator shaft and the diffuser casing. This labyrinth seal is pressurized with PCD air. PCD air being air coming off the last stage of compression. This prevents any oil leaking out here and entering into the airflow. Some of this PCD air will flow through the seal and mix with the lubricating oil. They mix together and both flow back to the tank. This is a relatively small flow of PCD air, unless the seal was in poor condition, allowing a high flow into the bearing area. This would be seen as a higher than normal lube oil tank pressure. Continuing on with the compressor, we see in this photo the compressor casing right hand side. The compressor casings are split in 2, which allow either casing to be removed to gain access to the blades and vanes. As stated, we are looking at the right hand side of the compressor. Right and left of the turbine is often used to locate components. Front, back, left and right are taken as though you are sitting on the top of the turbine facing the air intake. The borescope plugs are positioned so that when the borescope is inserted into the turbine, it does not crash with a rotating blade. The access hole will always be at a stator vane. For this part of the inspection of the compressor, you can use a rigid borescope or a flexible fiber optic one. The rigid borescope uses high quality mirrors and a light source. The quality of the view is much better than the fiber optics. The rigid borescope is used more commonly on aircraft turbines than on industrial ones. The flexible borescope gives better movement as you can move around once you're inside the turbine. It also can have various tips depending on whether you need a wide angle, a right angle, straight ahead, etc. There is a big range of tips that can be used. A tip, for example, in a combustion inspection would need to be a wide angle giving maximum amount of light as it is a large area you're inspecting. With the flexible borescope, you need to be so careful not to get caught on something. You can see that there isn't a borescope axis for every stage. There are 16 borescope inspection ports in the compressor section. There are 4 stages with 4 inspection ports in each. As you enter the borescope access hole, you can look forward and back. You will see the trailing edge of the rotating blades of the previous compressor and the leading edge of the next stage of compressor. For example, when you enter VGV3 and look forward, you will see stage 3 blades, and when you look aft, you will see stage 4 blades.